Okay, thanks for joining my talk. So I try. Yeah, my name is Reyk Floeter. I'm from Germany. I like being in Japan. And I'm from the OpenBSD project. I try to write the name in Japanese, so maybe it helps to pronounce it. But I only have a little bit knowledge about kana. So this presentation will talk about the VXLAN driver. It was quite a challenge to create a talk about just a single driver. But when I was considering talking about VXLAN, I figured out it's more. It's not just about the specific driver, it's about the work that we do and that I do to handle networking in the cloud environment. So VXLAN is just a single part of it, but fairly important one these days. And all of that is something I call the cloud networking stack, because it's all about internetworking. So you might wonder, why do I use this term cloud all the time? It's really about like clouds and little colorful ponies here in this case. We used to laugh about cloud when it came up as technical people, but these days everyone knows that it's unavoidable. So we have to take care about it in the BSDs and OpenBSD in our case. So the cloud networking stack is something I, roughly put into layers here. These are different areas we are working on and we're trying to improve. So on the virtual side, when we run in a virtual machine, we have some network interfaces. And in these network interfaces, I started the VIC driver, which is basically for VMware, the VMXNet version 2 network interface. Then David Gwynn, DLG, finished it. Then we have the VIO driver, that's the VirtIO framework that's used by QEMU and all its siblings, like Zen is supporting it as well. And is Beehive using VirtIO as well? Okay, so in theory we could use this when you run OpenBSD on Beehive, right? And then there's a new driver, VMX. I didn't write this one, but
what does that mean? Does that mean it works or it doesn't work? I know the answer.
No, it works. Well, my work in VMX was mostly making it KNF.
Making it readable.
But VMX is a VMXNet 3 chipset in VMware, and it's basically a virtual PCI Express Ethernet chip. So the virtual Ethernet is a different area. It's dotted the background because we don't have a working solution yet in this area.
Oh, we have bridge.
We have bridge, and bridge is okay, but it's not perfect, basically. So it's still a question mark. Should we further extend and fix bridge, or should we start looking at alternatives?
Good question.
But the alternatives are also not so, well, they're nice, but not for OpenBSD actually. For example, most of them use threads or stuff like that. In the SDN area, I will mention this later, but I'm doing some experiments in this area as well. VXLAN is a driver for virtual overlay networks. This was a quick implementation basically. NVGRE is almost identical, but just a different vendor invented it. And then we have VLANs, SVLANs, and all the VPN protocols. VPN protocols are also very important in cloud environments when you have managed services, for example, or platform as a service. So the company runs the data center somewhere in the cloud, and then you use VPN to connect to it, or you have road variants and so on. So I even see that IPsec is becoming more important once again after it almost disappeared because of the cloud interconnection. And these days, we stop trusting each other, right? So people want to secure their connections and don't use just GRE anymore. SVLAN is something I added a few years ago. That's basically the Q&Q VLAN variation. So you have a different Ethernet type, and you can tunnel VLANs through a VLAN. Yeah, and the upper layers we have routing domains. So I still didn't figure out if the FIBs in FreeBSD are comparable to routing domains. But routing domains basically mean you can have virtually multiple routing stacks in OpenBSD. So you can assign network interfaces to routing domains, and then all the ARP information and all the routing will be in that routing domain.
So you can use the same IP address twice.
For example, yeah, the same IP twice, and you cannot route between different routing domains without tricks. Yeah, tricks. That's a trick. Then we have PF to do the tricks actually, and where's the relation to the cloud? Well, in PF you can actually do very interesting tricks when you do routing domains, and then you basically have isolated networks with overlapping IP ranges. And I had firewalls for customers that were running one PF box with a few hundred different customers, and all of them had their own private RFC 1980 networks, and most of them were the same 10/8 or whatever. And then you can run them in different routing domains, and then use PF to have, for example, a shared service network, and do the tricks to get the traffic back and forth. So it's actually a really powerful combination of routing domains and PF.
Well, you can net between them, so they can talk to each other even though they're using the same.
Yeah, but they have to do BiNet, so that's it. And yeah, and then there's RelayD. RelayD started as a load balancing daemon, and but it can all kinds of protocol handling. We're working on more. We are reinventing the filter language to look more like PF. Maybe we figure out that this is a mistake after listening to Henning's talk, but I think it's the way to go. So RelayD will be much more powerful. Still didn't finish the filter language yet. I think I promised it last year, but it's a very complicated task. RelayD is used by some very large sites, and if I just break it, then they will have a problem. So VXLAN, as a first example, is a very simple protocol for so-called virtual overlay networks, and it's basically replacing VLANs. So VLANs are limited in different respects. So one thing is, for VLANs you only have 12-bit tags, so 4K of VLAN IDs, and in VXLAN you have a 24-bit identifier, so it's like 16 million virtual networks. So you might ask, why do you need so many virtual networks in your network? Once again, that's a cloud, right? So you have a cloud ISP, you have a lot of customers, and all of the customers use different VLANs, and then you quickly have at least more than 4,000 IDs. So for cloud operators, this is a requirement. And the other thing is that VXLAN is routed over IP. It's using UDP encapsulation of the packets. So in theory, you can create a virtual network between different locations and IPsec protected, for example. So in this case, you start scaling up more with the network IDs. VXLAN is not an RFC yet. The draft is written there. The latest version is version 8. VXLAN is defined by a consortium of different companies, but it's already in use. So they try to win a race here, and that's why it's not an RFC, but we care because like VMware, Nicira, they're doing it, and Cisco is doing it in their virtual switches and so on. So it is already important, and it's not even finished yet. So it might change, but the last versions of the draft only had like minor changes or spelling fixes. So to give an example how it might work is the gray boxes are the physical servers. So like typically a VMM running VMware, for example. And there you have your virtual server. The virtual servers are connected to the virtual switch of the machine. And then you have like a VTEP, a virtual tunnel endpoint. So this is typically the virtual switch, like OpenBSD switch, for example, or the Cisco Nexus 1000V. And then the virtual switch uses VXLAN to encapsulate the traffic from specific virtual networks from the customer and to pass the traffic to other tunnel endpoints, so physical servers. So you have your data center with all these different hosts, and then you can create basically your VLANs between them quickly. And the good thing here is that it's using UDP, so you don't have to take care that everything is in the same layer 2 network. It can be routed, it can be somewhere, and you can quickly scale it up. So VXLAN uses two different modes. One mode is multicast. So it basically you broadcast a packet to the multicast group, and then all listeners, all tunnel endpoints are receiving these packets. So this way you can create like a virtual layer 2 network. You send like a broadcast frame out, and it's translated into a multicast message that is sent out as VXLAN, and all the registered hosts are receiving it. And then it can also operate in unicast mode, so that when it knows the tunnel endpoint of a specific MAC address, it directly sends a unicast message to this endpoint. So this is also something that is not available in VLANs, in classic VLANs. So the VXLAN header is a 64-bit header, 232-bit words. So it's slightly larger than a VLAN header. And it is also combined with the additional outer Ethernet, IP, and UDP header. So from IP, UDP, and VXLAN, you can have like a protocol overhead of at least 50 bytes. In some cases, of course, it can be more with extensions, but that's just the encapsulation of it. And then below the header, you have like your original Ethernet frame, normally. The VXLAN header includes the 24-bit network identifier, and everything else is reserved, except this one flag,
the JavaScript stuff.
the I here. The specification says like this has to be 1 for whatever reason. That the virtual network ID is set flat. And it's always 1. So everything else is reserved for whatever reason. So let's talk about the implementation in OpenBSD. So David Gwynn from Australia, he's using OpenBSD in a large university network, and most of his machines are running on VMware ESX servers. And the additional evil is they have VMware and Cisco networking infrastructure. So he started a user-land implementation VXLAN because he wanted to connect his firewalls to the VXLAN network directly to be able to filter there without depending on a Cisco vSwitch. So you can just plug a physical machine, for example, in the network and join the VXLAN networks. His implementation was kind of an experiment and used, written in user space, and it was using the TON interface, like the old PPPD, but there we know it doesn't scale and we don't do that anymore. And it was very complicated for him to implement all the virtual endpoint discovery. So virtual endpoint discovery, let's jump back for a moment, is required if you jump from multicast mode, you send a message. If you don't know the endpoint of a specific Ethernet frame, and then you have to figure out, oh, this MAC address is somewhere at this endpoint. So we discovered it basically by learning it, and then we send a unicast message to it. Sounds a lot like a bridge, right? So there are some implementations of VXLAN that implement a very complicated framework for virtual endpoint discovery. And I looked at it and I thought, well, it could be much easier to do it in the kernel and just use the bridge code, because the bridge is basically doing the same. It learns the port, the network interface where a specific MAC address can be reached. So why are we duplicating this and giving it different names? It's the same that we had all the time with bridge. So the code is the VXLAN. It's 777 lines of code, so it's not so much. And then some small changes to UDP input, the bridge, and IF config. The initial driver was inspired by VESA, VLAN, but also the GIF and GRD tunnels. It's an Ethernet interface, but also a tunnel interface. And of course, it's using the OpenBSD ISC style license. So the VXLAN protocol, as I said, is simple. All it needs is this 50-byte header, basically, and then some handling. The most complicated part is the endpoint discovery. So I have the VXLAN header, which is like these two 32-bit words. You might wonder why I'm not using bit field, or we don't use bit fields in OpenBSD. for networking protocols for different reasons. So I have two 32-bit words and some masks and flags to quickly access it. But these VNIS flag has always been set, so it's not so hard to do. And on the right side, you have the IP4 version of it with the additional IP header and the UDP header. So this is like the minimum you need for VXLAN. So the network interface, I know it's very exciting, but it just works. The network interface is just a BSD cloner tunnel interface, so you can just ifconfig VXLAN. It's all done with ifconfig. You don't need a new tool except for the bridge part. Each time you create an address, you have a fake Ethernet address that's random. If you want to have a fixed address, then you have to manually set one. Like in OpenBSD, we do it for virtual interfaces that we create those random addresses at the moment. I think it should probably be changed to use a hash to have something that is reliable, but that's the way it was done for virtual interfaces in OpenBSD. One important note about the network interface is that the MTU is set to 1500 bytes by default. So it's not set to 1450 like on, I think Cisco did it, or some other vendor. And you might know it from like GRE or GIF, these old tunnel interfaces. When you create them, by default they have a lower MTU. And we actually talked about it, and we think it's a mistake. With VXLAN, even the standard says you should take care that your backbone is using a higher MTU, in this case of 1550 bytes, because it's an internal backbone in most cases, to carry VXLAN, instead of causing all kinds of problems by using a lower MTU on the tunnel itself. So the text here is from the latest draft, and most of the implementations use 1450 by default, but the draft actually approves that our implementation is right here. So multicast is also a very important thing. Henning, still multicast matters, but DVMRPD doesn't matter at all, but that's a different story.
Multicast between different ISPs plane doesn't exist.
Between ISPs doesn't exist.
Inside your network, different story.
Yeah. So by default, VXLAN is running in this unicast mode, so you specify a tunnel like you did on traditional tunnel interfaces, source address, destination address. When you define a multicast address as a destination, then the code will figure out this is a multicast address. Then the driver will register the multicast address on the underlying parent interface and send outgoing frames to this multicast address. So just by configuring a multicast address as a destination, you basically get an Ethernet hub. All messages are sent to all members listening to this multicast group. So the driver has to register the multicast group on the parent interface, and this is a little bit tricky because we don't have a real network interface, or it's not even a virtual Ethernet interface. It's typically running on top of another interface. So you have your VXLAN interface, and then the actual tunnel traffic is sent out of your EM0 or VMX1. So for multicast, the tricky part is here you have, when the address is registered in the kernel, you have to also register the multicast address on the underlying parent interface, like EM0. And then you have to track changes. So if the parent interface is like a VLAN, for example, or a virtual interface, then you have to detect if it's like going away and update it. Or if the parent interface IP address changes, you have to check, is it still the address for my multicast group? So getting the multicast part right is a little bit difficult. So we need two interface hooks that detect if the interface is detached, the addresses changes, or the link status changes. The link state shouldn't be required by multicast registration, but when you have VMware, you register a multicast group on the virtual interface, like VMX or VIC. Then I saw that when you suspend the virtual machine and resume it, which is also very normal in cloud networks, then you lose all your multicast associations. So VXLAN has to detect that something happened, and I detect it with a link state change and re-register the multicast group. The bridge integration is the next part to get the endpoint discovery done. So when you add it in with a multicast destination address and add it to a bridge, so VXLAN as a bridge, I will show a configuration example in the end, then the driver starts working in this dynamic mode, so that the bridge can learn tunnel endpoints for me, and if there's a known tunnel endpoint, then VXLAN will send it directly as a unicast message to the tunnel endpoint. So then we turn it from an Ethernet hub to an Ethernet switch. So I extended the bridge code a little bit, but the diff is fairly minimal, and it should be possible to adapt it to other bridge implementations without big trouble. So it basically sets PF tag on the received packet, the driver, so VXLAN, well, it's an MBUF tag, sorry. VXLAN receives a packet as a UDP message, decapsulates it, and then it sends it to the ether input routine, and it adds the MBUF tag with the original tunnel endpoint. So on the receive side, we get a UDP packet, then we evaluate, is this UDP packet for me, is it a VXLAN packet for me? And then, if yes, then we add a MBUF tag carrying the original IP address of the tunnel endpoint that sent me the packet. Then the packet, if yes, then it goes into the ether input, does all the usual things going in the bridge, and bridge checks, is this MBUF tag there? And if the MBUF tag is there, then it can store it in addition to the MAC address. It can store the saved tunnel endpoint address, which is basically just a sock address struct in the bridge cache. So this way, we can easily use the bridge like it is and just provide an additional attribute, basically, to the bridge cache. On the transmit side, so you want to submit send a packet. It's calling VXLAN start, and the output routine checks the bridge tunnel. So you start a packet, you remove the MBUF tag. First you get one. The bridge does this part by giving you the the bridge code sends the packet via VXLAN. The bridge tags it with the original tunnel destination, basically. Then VXLAN checks, is this tag present on the packet? And if yes, then we send it to this destination that was stored there as a unicast message, and if not, it's sent as a multicast message to the group. So the bridge retags the outgoing packet with the learned tunnel endpoint address. The IO-CTL interface is also very simple. We already have the existing controls for the GIF and GRE tunnels. Should be the same in the other BSDs, but maybe with different names these days. But they are used to set the source and destination address of the tunnel IP addresses. Then we have the extension in OpenBSD to set a non-standard routing table for the tunnel. I just added these new IO-CTLs to set the virtual network ID on the tunnel as well. I called it VNet ID to have a name that's not specific to VXLAN, basically. At the moment it's only used by VXLAN, but other overlay network protocols can use the same interface. So, and VNI is a name that's not very descriptive, basically. And the existing PHY address, that's the IO-CTL to set the source and destination tunnel address. I just extended them to accept an additional port in the SOC address struct that they're using. So, no complicated new interface to configure VXLAN. Okay, let me give you some configuration examples. So, the first one looks a lot like the configuration for GIF or GIE. I just changed the keyword to tunnel in the configuration and in the output of ifconfig. In some cases it used to be PHY address for whatever reason. It's not really a physical address, but no, it's just tunnel. So the first example on the left side, it's the same way you would configure a GIF interface, except that the VNet ID is a new option. So a traditional tunnel only has a source and destination, and then you can have only one tunnel between the source and destination. So with VXLAN you can create multiple tunnels between the same source and destination, just for different VNet IDs. And then you have an extension in the third example where you can also specify the destination port because it's using UDP. By default, it's using the 4789, the official port, but 8472 is a non-standard port that is used by Cisco, of course. In the last example, it's using a multicast address. In this mode, it will automatically switch the operation in multicast mode. On the right side, this is everything you have to do to enable the learning mode, the automatic unicast or multicast mode. Just you configure the interface with a multicast endpoint address, and then you add it to a bridge. It can be the only member of the bridge interface, but of course you can also add physical ports on the machine. But all you need to do is just to create a bridge and add it there. And then we have a virtual switch basically. And this is all it needs to configure it. So very simple. Looking at the other VXLAN implementations, you have like configuration files where you specify your endpoints and do mapping and so on. And this way, using the bridge code, it's very easy to do. And you have the benefit that you can also use PF and bridge filtering language to manage endpoint security, make ACLs of it, and so on. Future work about it. So NVGRE. NVGRE is another virtual overlay network that only exists because Microsoft wanted to have their own protocol. And if you look at the drafts, the NVGRE draft appeared 1 month after VXLAN. So VXLAN is like VMware, Nicira, Cisco, and a few others. And NVGRE is Microsoft, HP, and a few others. So I don't know. But NVGRE is using GRE instead of UDP as a transport protocol, and a slightly different header and different terminology, but in the end it's basically the same. The VNI is called VSID. That's also a reason why we just have VNet ID, one name, and not one for protocol. And it's very easy to add NVGRE support. We just need the GRE key support. GRE key is already a part of the official traditional GRE standard. And I think FreeBSD already has code for it. I once looked at it. Then NVGRE would need to support these new I/O CTLs that I added. And then use the bridge interface to do the endpoint discovery. And the multicast handling, but this is also not so hard. So we didn't do NVGRE yet because it's very hard to test. The only official implementation we found was Windows Server, and configuring NVGRE on Windows Server manually is just very, very painful. So we gave up and worked on more important things. But let me know if you would need NVGRE or if you ever used it. I think VXLAN is the more important protocol. So for VXLAN we have to support IPv6 as a transport protocol. It's v4 only at the moment. Within the tunnel, of course, you can use anything that is going over Ethernet, but the transport is just IPv4. For the UDP receiver. At the moment, the UDP input function in the network stack is checking if VXLAN is enabled, then it sends it to the VXLAN function that it's checking, or is this packet for me? So this is quite some overhead if it's done for each and every UDP packet. And it's something that is already done on the UDP socket part. So we don't have a mechanism in OpenBSD that allows to create kernel-based UDP servers, basically. And I'm not sure if it's really required. At the moment we have two cases, that is VXLAN and the IPsec UDP encapsulation. And then potentially pflow, but pflow is just sending and not receiving. So maybe there's a way to add it to the UDP socket handling, but UDP socket handling always assumes that you have a process context that we don't have. So it's not easy to do it, so I ended up just adding it to the UDP input function directly, but it's not affecting the performance unless you enable VXLAN. Otherwise, it's just in simple if VXLAN enable, and yeah, then it's skipping it. Yeah, for the bridge code, we have to improve our bridge. There's another reason for bridge. For example, if you run multiple routing domains on one machine, then it might be nice to connect these routing domains with a bridge to pass traffic between these routing domains. At the moment you have to use a PF trick, and no, it does not work with bridge. No, for 2 years I say it doesn't work, but some people don't believe me in OpenBSD, but it does not work.
The message didn't reach me.
Yeah. So it does not work, basically. I had a diff for vEther to interconnect two vEthers, basically like a crossover cable. It's a very simple diff, but for some reasons it's not going into OpenBSD. And the bridge part is not working. So the PF trick is the only option at the moment.
When you say improved bridge, what do you mean? Like, what are you missing?
Again, bridge is not designed for something that you do. There are different things. So with bridge you cannot interconnect local interfaces, like between different routing domains, or for example, if you have like something like a host running multiple virtual machines on it, what we don't do on OpenBSD except with QEMU, then you could not use our bridge code, because our bridge code has a special handling for local traffic, and it's really hard to change this, because our bridge is very fast in that respect that it basically works on the Ethernet interop level, where it directly processes the packet. And that's not very easy to change bridge to interconnect virtual interfaces. Just by design, that's a problem. Another thing is, what the other systems do is when you have a virtual switch, like OpenVSwitch, for example, what people want to use, then they use the possibility to basically say you have your bridge, but you allow a user space process to make the decisions. And like so you decouple bridge and FIB basically. This cannot be done in OpenBSD at the moment, and there is work in NetBSD to do it, and there is work in FreeBSD to do it, and we may end up with like different implementations for license reasons, for I don't know, policies, whatever, but every system is going in this direction. And Linux, they completely rewrote the bridge for the same reasons. And then the last thing that we also need someday is an OpenFlow controller. The existing ones that I looked up are really crazy, like written in Java or in Python. There's one C version. The initial Nicira controller was written in C, but it's kind of end of life, and it's also not so nice code. The guy who wrote it sold his company, I think, for $1.3 billion, so he's probably not interested in writing this code anymore, I don't know. So I played a little bit with OpenFlow, and it's actually fun to see that my system is controlling OpenVSwitch or maybe the old Procore switches. It's kind of a fun story. HP bought 3Com, and then they tried to discontinue the HP switches, the Procore brand, until they figured out that the Procore switches were able to do SDN, like support the OpenFlow protocol. And these days, all the strategy of HP is about SDN and OpenFlow, and the old Procore switches are basically the ones that are more important for that. And I know personally that they kicked out most of the architects and engineers from the Procore project, and now they're trying to get them back, which is not so easy. And then there is NFV in the cloud world, network function virtualization. That's actually funny. There's a consortium, a committee, that they're defining NFV. And the whole idea is that instead of using a hardware router, you define functions and use them in software-based routers. That's their innovation, and they have a committee about it. And so in the beginning, the initial specification of NFV was basically just that. We use software routers. Great idea. Now they're trying to find some protocols or something to make it really unique. Whatever, like maybe the possibility to run scripts on it, or I have no idea. But really, one a salesperson asked me, "Oh, do you support NFV?" And then I looked it up, and it's basically just doing routing and software. And I said, "Oh, yes, we are the NFV platform, right?" So, conclusions. So VXLAN is a complex protocol if you look at the endpoint discovery and all the people who wrote the paper, maybe 10 people wrote the VXLAN draft and the endpoint discovery. But it was very easy to implement because we had most of it already in our stack and maybe in the other BSDs as well. So it shouldn't be too hard to port it. Let me know if you're planning to do it. I heard, at least from some previous users, that they would like to use it. But you can also reinvent it, and then we do interoperability testing. I don't care. So the cloud introduced some new networking protocols, and we have to update OpenBSD in different ways to handle that one. We had to add MPLS and VRF support because all the users of internal routing were asking for it and say, "Oh, it's mandatory." And now these days we need like overlay networks, maybe SDN and some other features as well. Yeah, and I think OpenBSD is a really good choice for NFV to get like fewer cloud ponies, basically, the one I saw showed in the beginning, because most of this code is really scary. If you look at the SDN controllers that are written in Java by some students, and then they left the university 2 years later, and a big corporation took the code and made a product out of it. That's the quality of the SDN controller. And then large corporations are depending on this poorly written code. So we need better code in this area. So putting it all together it's the main fun, and then you can have some really interesting possibilities. Yeah. On the other hand, in OpenBSD, we are focusing on virtualization from a networking perspective, so we are not trying to really virtualize the running system. So we don't have anything like jails, and as I heard just I think today, no VNet is better because you have no VNet problems, and then PF still works, and so we're not going this way of like segmenting the kernel into these different areas. Maybe for virtual machines. Do you have questions?
So with the VXLAN and having to use multicast to broadcast, if I have two different data centers with virtual machines in them and I want a VXLAN between them, how does that work when you can't use multicast?
Then you can use unicast mode, just simple as that. Between two endpoints, then you just do unicast, and then the endpoint can just send it in the local network. And then you can use additional endpoint to multicast it into your data center network. But if you have a unicast destination, then you just specify your tunnel as source IP address, destination IP address, and not multicast address, and then it's unicast mode.
How does that work if I have 3 data centers?
When you have 3 data centers, then you can use multiple VXLAN interfaces and add them all to a bridge. And then the bridge code will figure out which port which is actually the same. So you can mix VXLAN interfaces with traditional bridge ports on a bridge. Or you can use multicast routing. Yeah, that's true. Any more questions? Okay. So, thanks.